Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let's compute the limit of a logarithmic function, logarithm of x, as x approaches to 1 using the table of values. Before we start coming up with a table, of course, let's establish this idea. Our given function identified here is the common logarithm of x, or you could also interpret this as a logarithm of x to the base 10, because if there's no clear base, automatically it gives us logarithm of x with the base 10. We will have a separate video for the natural logarithm of x, but they follow the same concept, the same idea, because we need to establish the table of values from both sides, from the left of the value of 1, because you will have here the limit of the said logarithm of x as x approaches to 1. We need to establish the value or the table of values from the left of 1 and from the right of 1. And if the limit for both are equal to each other, then we can proceed that, deciding that as the limit of our given function here. So let's start with the values from the left of 1. So let's have here x and f of x. You can try values from the left of 1 given that it is actually greater than 0. That is because the logarithm is just a transformation from an exponential function, and for an exponential function, whatever the value of the exponent, it can never give a negative result, because if the exponent is negative, you just simply apply the law of negative exponent, but still the value would become positive. So 0 and negative values are not included for all values from the left of 1. That is just my point here. Hence, we cannot use 0 here, but we can use values greater than 0 getting or approaching to our 1 from the right. So let's have here the smallest value, or this value, representative value, greater than 0 from the left of 1. If you're going to plug this in on our given logarithmic function, logarithm of x, you will have an approximate value equal to this. You have negative 1.0000. Take note, I am using here 4 decimal places just to establish the number of decimal places. I'm also going to write here as we try other values from the left of 1. So with this, we cannot actually predict the value. So let's try other values from the left of 1, now greater than 0.1. Let's try here 1/2 or 0.5. You may use your calculators there. As you plug this in on our function, you will have this approximated value, negative 0.3010. Again, you may use your calculators if you're still wondering what these values are. Now, it's not yet enough for us to have these two values. Let's try 0.9. Take note that the values now of x is getting closer to 1. Okay, but it's not equal to 1. So let's see the trend. As you plug this in our given function, you will have the approximated value of negative 0.0458. Okay, you might see a pattern here, but let's add more because we can plug in here more values from the left of 1. So you could have here 0.99, right? As it gets closer to 1. Or you could also add here 0.999. Okay, so as you can see, it gets closer to 1 now. As you plug in 0.99 in our given function, you will have an approximated value of negative 0.0043. And as you plug in 0.999, we will have here negative 0.0004. Take note, again, as x approaches to 1, okay, from the left, your f of x is also approaching a certain number, And if you would like to add one more here, 0.9999, you might even see it better. You will have here a value equivalent to this, or approximate 0.0000, but let me add another place for me to verify your understanding. So you will have here 4. Clearly, the value of f of x is getting closer to 0. Okay, so let's try. This is now the limit from the left of 1. Let's now try the values from the right of 1. Of course, since the right of the positive values from the right of 1, even infinity, are all part of the domain of this function, so you can try many values in comparison to what we did from the left, because 0 and negative values are not possible. So let's try here, let's say an integer 2. Plug that in on our given function. Using your calculator, you will have an approximation of 0.3010. Okay, so it's very small, but at least we can see this getting closer now to 1. As we have here the next value, let's say 1.5, you will get an approximated value of 0.176 and then 1. Okay, so we might see there is a pattern now. Let's add more to solidify our understanding on the trend. So let's have here 1.1, values like 1.01, getting closer to 1. Okay, you will have 1.001, even 1.0001. Plugging in all of this one by one on our calculator. For 1.1, you will get here an approximated value of 0.041 and then 4. For 1.01, you will have here 0.0043. For 1.001, you will have an approximated value of 0.0004. Similar thing, or almost the same thing, what happened to our values from the left, it gets closer now to 0 as x approaches to 1. But since I added one more for final value, let me plug that in. You will have here approximated value of 0.0000, but let me add another decimal place, 4. Obviously, this is getting closer to 0. Now, the limit from the left is 0. The limit from the right of 1 is also equal to 0. The limit for both sides are the same, and they are both equal to 0. This means that the limit of logarithm of x as x approaches to 1, since both sides are equal to one another and equal to 0, this is also equal to 0. This is how we illustrate the limit of the logarithm of x, an example of a logarithmic function, again with base 10, as x approaches to 1 using table of values. So what are you waiting for? Subscribe now!